All right, as I was saying before I got cut off, you want to know how the speed of the ship at the bottom of its motion is related to the angle that it swings down from, okay? The angle, again, is being measured from equilibrium up to its highest point. You know that the speed will increase with an increasing angular displacement theta, but you have a sneaking suspicion that somehow this is moving around some sort of circle, but there's angles involved. Treg's got to be involved somehow, trigonometry. So you predict that as the sine of the angle theta increases, the speed v increases as well. Is this reasonable? Explain why or why not. So this seems like kind of a weird question, and a lot of you, I think, if you didn't know how to solve this already, you would kind of sit there and stare at it and go, oh, I have no idea. Think about what the sine of theta would look like. You know what the sine equation looks like. You know what the graph of sine of theta versus theta looks like. You know that a sine shape, this shape of the sine graph, it starts off at 0, goes up to 1 at 90 degrees, goes back to 0 at 180, goes to negative 1 at 270, and is back to 0 at 360. You're very familiar with the sine shape. Now think about how that applies to this situation. Think about how the pirate ship works. The higher you bring it up, the faster it should move, right? Well, that's true up to a certain point, and that point that it's true up to is 180 degrees. If you lift this past 90, the speed should still increase. Now think about the sine equation. Does the value of sine theta still increase when you go past 90 degrees? No, it doesn't. 90 degrees is the maximum of the sine equation. So if the speed was somehow related to that equation, then what you would expect is if the speed is somehow related to sine theta, what you would expect is the sine theta equation to maximize at 180 degrees if this is swinging from the highest point down. But it does not. Therefore, these can't possibly be related. So our answer, and I'll prove this to you in just a second, this is not reasonable. Since this would predict a maximum speed if the ship had an initial angular displacement of 90 degrees. Okay, just like the sine equation, sine is maximum at 90. If the ship had the fastest possible speed when it swung down from 90, this would work. But we know it doesn't. If you go above 90, it should swing down faster. Think about it, conservation of energy. Okay, more gravitational potential energy, more kinetic energy at the bottom, it moves faster. In reality, the ship should gain the most speed if the initial angular displacement is instead very close to 180 degrees, making this prediction inaccurate. So the idea is, we thought about a potential relationship. We thought about how the speed should change, okay, as we increase the angle more and more. We know that it gets, the speed would be biggest if the initial angle of displacement is 180 degrees, but this doesn't match up with our equation for sine theta, okay? Sine theta is not a maximum at that point. Sine theta is maximum at 90 degrees. Therefore, this doesn't fit. If you want proof of this not fitting, if they were related, okay? If they were related, then we should see some sort of relationship if we were to graph the speed versus sine theta. And that's actually what I've done on my computer. I'm going to take you over and show you the computer now. Ignore the Black Death book. Okay, we see that we have angles going from 5 up to 165. We have speeds, and these are just So let's say I filled in speeds. Let's say you took this data. The angles, the signs of those angles are given over in that right-hand column next to the two blacked out columns. And here's the graph. This graph is not at all linear. This graph doesn't, it's not even a function really. It doubles back on itself. So we see that these two are not related, okay? Not related in the way that we think they are. As the speed increases, the angle, or as the angle increases, the speed does not increase, okay? It doesn't, as the sign of the angle increases, the speed does not. So this cannot be a possible solution, okay? Let's get back and centered over here. So our job, obviously, if you looked at the back of this, is to find some sort of solution to this problem. So let's go to the back. And we get caught up here sometimes when you guys try to linearize stuff. When it says derive, you guys see this word derive and everyone freaks out. Derive the actual equation or actual relationship between the initial angular displacement theta as measured from equilibrium and the speed v at the bottom of the ship's path. When you see derive, it doesn't mean, okay, you've got to come up with something like crazy. All you've got to do is think about, okay, well, how would I figure out the speed based on this variable they're giving me? Okay, how would you figure out the speed normally? I think for a pendulum, a lot of you would think, hey, okay, the acceleration of this object is very clearly changing. All right, the forces on it are changing directions all the time. Forces probably isn't a great idea for this. Instead, why don't we look at energy? Why don't we look at using the conservation of energy? As I kind of alluded to before, there is some initial gravitational potential energy that gets turned into kinetic energy. We know the equation for gravitational potential energy is mgh, and I'll put a naught because it's initial, equals 1/2 mv squared. Now what can happen here? I could lose both masses. If I want to solve for the speed or get the speed by itself, what I really need to figure out is how the height relates to the initial angle. Okay, so I'm going to draw a little picture over to the side here. Let's say that here is the pendulum. Let's say it's straight down. Okay, that long. But initially, the pendulum is, let's say it's up here somewhere. Okay, and it doesn't matter what angle you draw it to. But the tricky part here is since we're allowing angles of up to 180 degrees. Now in real life, would a pirate ship do this? No, but maybe we have seatbelts on this one. Maybe we, maybe this is a thrill ride more than just kind of a gentle ride. The angle theta is this angle right here, okay? And our job is to determine how big this is, how big h naught is in terms of theta. What we do know is that this down here is L, and this up here is L. It might be easy to start with equations, to start thinking about what would happen if we just had a normal displacement, like less than 90 degrees, okay? What has it been like when it's been less than 90 degrees? I think in the past, I'll draw another one up here. No, you can't see that. Hold on a sec. Let me find space for one. Okay, here's how it's been in the past. What we've done is we've said, hey, look, we kind of have a triangle right here. All right, where we have this is L. This hypotenuse is also L, and we're looking for this. So this side length has always been L cosine theta. We've done L minus L cosine theta. So in this case, the initial height that's needed is L minus L cosine of theta. Let's see if that works here. Okay. Does L minus L cosine theta work up here? Well, it seems like it might not, but I want you to remember something about the cosine, the value of the cosine function. Cosine starts out at positive, when the angle is 0, cosine starts out at positive 1. It then goes down to 0 at 90 degrees, then becomes negative 1 from 90 to, or it becomes negative 1 at 180 degrees. If you do cosine of 180, it's negative 1, which implies that between 90 degrees and 180 degrees, you have a negative value, okay? So if we use this equation, L minus L cosine theta, we have the initial L here, and then we also, since we have minus L cosine theta, if the cosine is going to be negative anyways, then you have a negative here that's going to work with this negative. This is actually going to turn into a positive, and it's going to be the positive angle It's kind of weird to explain, but it's gonna be it's gonna add together, which is kind of strange. So let's start with this right here, and you can verify all this on your own. Let's see if this will work. H naught equals L minus L cosine theta. At 0 degrees, okay, at 0 degrees, then you have cosine of 0 is 1, L minus L, the initial height is 0. Makes sense. What about at 90 degrees? Well, at 90 degrees, you'll have L minus L times cosine of 90. Cosine of 90 is 0. Anything times 0 is 0. You just left with L. If this was displaced from 90 degrees, yeah, the initial height of the pendulum is L. Makes sense. What if we go all the way up to here, 180 degrees? Well, how much of a displacement is that? You've got L here, and you've got another L straight up. That's 2L. Cosine of 180 is negative 1. That extra negative will turn this into a positive. Your initial height is 2L. So at the three most important heights, three easiest to look at heights, you've got an equation that seems to match up. I think that's a pretty good clue that this is actually the equation that describes how high up the pendulum is in terms of theta and L. So we're going to go with that. And if this is actually true, then we should be able to eventually graph something that looks like a straight line, like we're trying to get to. We should be able to get a smooth, nice relationship if we graph the right things. Okay, so if we graph the right things, we should be able to use whatever equation we come up with to predict some things that maybe, and then check them, to make predictions and then check them. So ultimately, when we get down here, we're going to see if our equation here, L minus L cosine theta, works for all of these angles. Okay? So instead of writing H naught, we're going to substitute in G, parentheses, L minus L cosine of theta equals 1/2 V squared. I want to get V by itself, more or less. So I want to, let's see, bring the 1/2 over to the other side. That becomes V squared equals 2G L minus, 2GL minus L cosine of theta. But here's the tricky part. All right, what are our variables here? We want to know the relationship between theta and V. All right, right now we've got the theta, it's kind of tied up with a whole bunch of other stuff. It's inside parentheses, there's something outside. Let's distribute this and let's rearrange this a little bit. Let's instead write this as V squared equals negative 2GL cosine of theta plus 2GL. So I distributed the 2G to both terms, and I flipped the order of the terms, and that'll be apparent in just a second why I did that. We want to try, eventually down here, to make a linear graph showing the relationship between V and theta, okay? Or at least what we should graph to show their relationship, all right? This is a linearization problem. Now, if I have the equation, if I want to get to a straight line, I know that equation is y equals mx plus b. Y and x being variables, m being the slope, b being the y-intercept. X is my independent variable, y depends on that. In other words, x is sort of like, well, what I'm going to base it on is theta, okay? I'm going to base it on theta because that's what I control, is the angle. V is what I'm looking for, the speed. Now, if I were to make a graph of just V versus theta, I already did that. If I were to just graph this, let me show you what you end up with, okay? So let's bring you over to the computer again. All right, there's our old graph. I have another graph under this one, so let me delete that one. Okay, here's the graph of V versus theta. All right, there's my two variables, V and theta. Here's a graph of V versus theta, and at first glance you might say, hey, this looks pretty linear. But you could also make the argument that there is a curve to this data. And I think the more you look at this, the easier it is to see the curve, okay? Kind of going like this. If we were to continue this, it might curve even more. And that's not what we would want here, okay? So, and another thing, if you look at that r squared value, it's pretty high. R squared tells you approximately how well the data fits the trend line, 0.9649. We can do better than that. 0.96 is pretty good, and you can see the data points don't lie that far away from the line, but the best r squareds are usually like 0.99 something, all right? So this isn't a terrible one, but it's not the best. We're going to come back to this. We're going to see if we can figure out something else to graph this with, not v versus theta. Okay? So we have our graph, we have our equation, y equals mx plus b, and we can start to do some matching. Very clearly, y matches up with v squared, okay? Y is our variable that we're looking for. V squared, we can't really separate that squared from, we can't really, we can't do anything about that squared. So for right now, what I'm going to do is I'm going to say these two are matched up. By the way, let me just put this in a box. This equation right here is the derivation. It's nothing harder than doing an energy conservation and saying, hey, here's the equation that governs what's happening here. The trickiest part was doing this, and that, I will grant you, is tricky. Let's look at our independent variable. We're changing theta, but look what that theta is attached to, okay? You can't just take this theta out and say theta is x because it has the cosine attached to it. If you just take that out, what's that cosine supposed to be doing? Maybe we should be graphing as the independent variable the cosine of theta. Okay, maybe we should be graphing the cosine of theta. If we do that, look what we're left with. Negative 2gl matches up with, because it gets multiplied by x, our slope. Notice that a slope in a linear graph is constant for a linear graph, and negative 2, g, and l are all constants. Same thing for our y-intercept. Our y-intercept is positive 2gl. So we've matched this up, and if we were going to graph something, it shouldn't be that we're graphing v versus theta. We just saw the graph of that. It's not as linear as we thought. Maybe we should be graphing v squared versus the cosine of theta. Now, what I would do is take a few minutes, fill in this data table, and then when we come back, I'll check that with you, and I'll show you the graph that we made and how we can check to make sure that this equation, based on this math right here, is accurate.